Hello and welcome. Today we're going to be discussing the problem lineup queries. In this question, we are given a long line of cows, and at every moment in time, the first cow jumps halfway through the line of cows, and a new cow T joins the end of the line. And we want to be able to answer two different types of queries about this long line of cows. The first type we want to answer is where is cow C at time T? And the second query type is what cow is stored at position X also after time t. And the biggest hint that we have for how to solve this problem is that we can see that t is very large. T is 10 to the 18th, so we're going to essentially have to find some sort of math formula in order to solve this question within the time limits that we're given. And here you can see an example of what the cows look like for the first 25 or 26 moments in time. And if you want to pause the video, you can start to see that there are a great deal of patterns in this data. And we're going to exploit those patterns in order to find our math formulas. Now we're going to solve each query separately. So we're going to solve the query one, write the code for query one, then we're going to solve query two and write the code for query two. One thing to note about this question is you did get partial credit if you were only able to implement one of the two query types, so that's always nice to see. In query one, we want to know where is cow C after time t. So let's take a look at some examples. Let's start with the query 4.4. So this is saying, where is cow 4 after time t? We can look at our data here and see that cow 4 is at position 4 after time 4. The key idea is that the positions are 0 indexed here. So it's the fifth cow, which is in position 4. If we look at the next query, query 4.7, this is asking where's cow 4 after time 7. So if we look at time 7 here, we can see it's still in position 4. It actually hasn't moved yet. But after time 7, it's going to move and its position is going to decrease. So let's take a look at the next query. This is 4.11, and this is saying where is cow 4 after time 11? If we see time 11, we can see that cow 4 is in position 0. It's just about to jump. And at the very next moment in time, it is going to jump halfway through the values, and it's going to end up at position 6. So at time 12, it jumps halfway through the array and lands at position 6. What's interesting is that the amount of time it takes to jump again is going to be its current position plus 1. So if I'm currently at position 6, the next time I jump is going to be exactly 7 units away. So let's take a look at some key observations. The first key observation we made is that there's a great deal of time where the cow's not moving. For the first 4 moments, the cow doesn't exist. For the next 4 moments, the cow stays the same. No one's jumped over it yet. And then for the next 4 moments in time, the cow's position is decreasing, but it hasn't yet jumped anywhere. The next observation is that we saw that the first jump occurred exactly at time is equal to 3 times the cow's value, right? So cow 4 jumped exactly at time 12. If we were to look at cow 5, we'd see that cow 5 jumps exactly at time 15. And you can pause the video and see that this pattern holds for all of the cows. And where did it jump to after that moment in time? Well, it jumped to position 3 times c over 2, right? That was just the current time value divided by 2. And then the final observation, and the most critical observation, is that the time until the next jump is always the current cow's position plus 1 after we make it through these edge cases. So what this allows us to do, this fifth one here, is it allows us to come up with a math formula that is going to predict the amount of time until the cow jumps next. And I can just skip to the next jumping point of the cow until eventually I reach time t. So I'm just going to, instead of sort of iterating 1 unit of time at a time, that's kind of a weird sentence, I'm going to instead skip to the jumping moments, and that's going to allow me to process these queries much faster because I can't afford to loop over 10 to the 18th moments of time. So we're going to use this fifth observation that the time until the next jump is always my current position plus 1 to calculate my future position. And I'm going to keep doing this until eventually I reach time t or something close to t where I can sort of calculate the exact position using math. So let's take a look at the code for query 1. We're going to start by filling out our edge cases, right? If t is less than 2 times c, we're just going to return c. The cow hasn't moved. And then the second edge case is that it hasn't jumped yet. So if it hasn't jumped yet, we can calculate its current position as basically like how many moments of time have passed since it started moving. And it's just going to be c minus those values. So if it's been 1 moment, it'll be c minus 1, then c minus 2, then c minus 3, c minus 4, and so on. If I'm not in one of these edge cases, then I have jumped, and I just need to see how many jumps does it take until I reach approximately t. So what I'm going to do is I'm going to create a variable called ct, which just represents the current time, and pause is going to represent the position, right? So our first jump happens at time c times 3, and its current position is exactly half of that. So the amount of time it takes until the next jump is going to be pause plus 1. So what I'm doing in this while loop is I'm just going to see, can I fit one more jump without exceeding t? Do I have enough room to jump again before I hit t? If I do, I'm going to jump that far ahead in time, and then I'm going to update my position to wherever I jump to. And remember, the position I jump to is just the current time divided by 2. So whenever I jump, the position I jump to is just t over 2. And I'm going to keep doing this over and over and over until the next jump would force me to exceed t. Because once that happens, I know that my final position is going to be somewhere along this diagonal, and I just need to calculate how many steps along this diagonal until I reach the final moment in time. So there are no more jumps once this while loop finishes running. And we can do that with a simple formula. So we're going to take our current position, and we are going to subtract off whatever is remaining in the time. So CT is the time I've used. T is the total time I want to simulate. So the difference in these values are sort of how many times my position is going to decrease. Remember, every moment in time decreases my position by 1 unless I'm jumping, but there are no more jumps. We're now ready to begin looking at query 2. So in query 2, we want to know what cow is at position X after time t. So just like before, we're going to look at some examples. If we had 4, 7, this is asking what cow is in position 4 at time 7. In our grid here, we can just take a look at time 7, position 4, that's cow 4. So our query type answer is 4. If we were looking at 0, 11, this is asking what cow is in position 0 at time 11. Again, if we have this table of values, it's really easy to answer these queries. We just go to time 11 at position 0 and we see it's a 4. Next up, if we have query 6, 12, or 22, this is asking what cow is in position 6 after time 22. If we go down here, we can see that the cow in position 6 is cow 4. But how can we begin approaching this problem? There are sort of two cases that I want to focus on. And the two cases I want to focus on are going to follow a very important line through the data here. So I'm going to draw this orange line. And this orange line represents the first moment where a cow starts moving. So if you are to the left of the orange line, you have already moved and you're all jumbled up. If you are to the right of the orange line, you haven't moved yet. And since you haven't moved yet, answering what cow is in that position is super easy. It's just cow X, right? So if the cow hasn't moved yet, cow X is in position X. So the only challenging case is working through what happens to the cows that have moved. And the key idea is we want to jump backwards in time until we reach precisely a value along this orange line. And this orange line corresponds to 2 times x being equal to t plus 1. The key idea, if we were to draw out the path of 4, we can see that 4 starts along this diagonal, goes up, hits the orange line, teleports to the beginning, goes up, hits the orange line, teleports to the beginning, and then lands exactly on the orange line. And we can see this is where 4 started from. So we want to trace out this green path in an efficient manner. So what we're going to be trying to analyze in this question is sort of how can I work out when the cow is going to jump back to position 0, and I'm going to calculate just over and over and over. When's the next time they jump back to position 0? When's the next time they jump back to position 0? And then finally, I'm going to stop when I land precisely on the line 2x is equal to t plus 1. You can think of this as sort of the opposite of the other case. The query 1 sort of math formulas worked by jumping forward in time. The query 2 math formulas are going to work by jumping backwards in time. So when we're actually jumping backwards here, there are going to be 3 different cases. The first case is the easiest case. If I am to the left of the orange line, then it is very easy to calculate where I'm going to end up next. Let's take, for example, this 4. Since this 4 is to the left of the orange line, what's going to happen is as I decrease time by 1, the position is going to increase by 1. So if I'm to the left of the orange line, every time I jump backwards 1 step in time, the position increases by 1. If I decrease or increase my position another time, you're going to see that I jump past the orange line. If I jump past the orange line, then this inequality is going to be true. So 2 times my position is going to be strictly greater than t plus 1. If I jump past the orange line, that means my position should reset to 0. And I'm going to then be back to the left of the orange line, and I can repeat this process. And you can see that when I cross the orange line again, I'm going to jump back to position 0, and I'm going to repeat this process again. And then eventually, I'm going to land exactly on the orange line. So I'm going to land exactly such that 2 times my position is equal to t plus 1. And when I have reached that time, then I can just return my current position because that is the time where the cow has actually entered the equation, right? So that's the moment in time where cow 4 is just about to start moving. So we can trace through another example here. Let's say we're looking at cow 6. Again, we can start at cow 6, go 1 unit of time backwards, then we're going to cross the orange line. We're not on the orange line, so we jump back to position 0. Then we go back, and we can see that once we land exactly on the orange line, we can just return position 6. So what we can do is we can just simulate going backwards in time until eventually we fall exactly on the orange line. We don't want to do this 1 step at a time, just like in the previous query, because that's going to be too slow. So one way we can speed this up is again by applying math. So the math that we want to do is we want to solve this equation. So we want to find how many steps A does it take us until we are past the orange line. So exactly on the orange line or somewhere to the right. And if you solve for the minimum value of A that satisfies this equation, you end up with this formula. So at any moment in time, we can calculate the number of steps it takes us to cross the orange line by jumping A steps. And we're going to keep repeating this over and over until we fall exactly on the orange line, and we will return our current position. So let's see if we can implement this. So we're going to start here on query 2. Again, we have this first edge case where if we just start to the right of the orange line, then our cow hasn't moved yet. We can just return our current position and everything is good. However, if we start to the left of the orange line, then we have to do this process where we jump backward until our position is exactly at 2 times x is equal to t plus 1. So we're going to jump ahead to the first place where we cross the orange line. Again, we're calculating A using this formula. You can work out the math yourself to see that A is indeed the minimum value that satisfies this inequality. So we're going to increase our position by A, and we're going to decrease our time by A. So we're walking backward A steps through time. And then we're going to check, have we fallen exactly on the orange line? If we're falling exactly on the orange line, the process is over and we can just return our current position. But if we don't fall exactly on the orange line and we've actually exceeded t plus 1, then we're going to reset x to 0 and apply this same formula. But if x is 0, the formula simplifies slightly, and we can just see that a becomes t over 3 plus 1. So the key idea is that at any moment in time, we're jumping back roughly t over 3 moments in time. So this is going to decay exponentially fast, which is exactly what we want when we're trying to travel through 10 to the 18th different time steps. So what this means is that x is going to be set to exactly t over 3 plus 1, and then time is going to decrease by that number of steps, right? We're traveling from position 0 to t over 3 plus 1. Again, we're going to check, have we reached exactly the orange line? If we haven't reached exactly the orange line, we're going to repeat this process again and again and again until eventually this equation is true and 2 times my position is exactly equal to t plus 1. And then at that moment in time, we can return x. And a good question that will probably be going through a lot of people's heads at this moment is, what is so special about 2 times x plus t plus 1, or is equal to t plus 1? And this, again, is just the idea of representing the first moment in time where a cow starts moving. So when this equation is true, this is right before the cow starts moving for the first time. So here's like 4 starts moving for the first time right after time 7. Cow 7 starts moving right after time 13. So when this equation is satisfied, that represents the moment in time the cow is about to start moving. And the reason we care about the moment in time where the cow is about to start moving is for all of the moments before that moment in time, the cow hasn't moved. So the position and the cow are actually the same value. So that's what justifies just returning our current position, because after that moment in time, anytime we go before that, it's just going to be the same cow in that position. So that completes the second query, and that completes the second part of the problem. So we're now done. If we run this code, we should pass all the test cases. Again, a pretty tricky math problem, but I think a very satisfying solution.